Welcome back to the course Basics of Mechanical Engineering 2. We are discussing manufacturing processes in this course. The last and this week is focused on casting processes. We have seen certain basics of casting, the design of sprue, gating systems, certain analytical models which are there when we try to solidify the molten metal so that the casting is finally obtained. I will walk you through certain problem statements so that we understand the problems which are discussed in the previous and this week are more clear for you. So, this is a tutorial session on casting. Let me just go through the concept of solidification shrinkage once again. There are 4 stages. Stage 1 is contraction of the liquid before solidification during cooling. This contraction causes further reduction in the height of the casting. This is just the revising of the things that we have discussed. Stage 2 brings a second effect where the top center portion is the last to get freezed. So, this is contraction during liquid to solid phase change. Solidification front has started at the mold wall. So, this is stage 2. So, this will be converted into shrinkage cavity. Then comes stage 3, where contraction of solid metal during cooling to room temperature happens. Effect is this shrinkage is determined by the solid metal's coefficient of thermal expansion, that is K. So, reduction in height due to solidification shrinkage and shrinkage cavity, you can see the cavity that has developed here, liquid metal and solid metal is there. Next is the last stage. Once solidified, both height and diameter contracts, resulting in shrinkage cavity at the top center. This is the shrinkage cavity, and also we can see something as a pipe in case casting is done in a tube like container which does not have mold wall at the bottom. Solidification shrinkage occurs almost in all metals because the solid phase has higher density than liquid phase. Okay, let me now just walk you through a problem statement so that we understand solidification shrinkage and try to see how does it lie in the cooling curves as well. The problem says while cooling a cubical casting of site 40 millimeter, it undergoes 3%, 4% and 5% volume shrinkage during liquid state, phase transformation and solid state respectively. Find the volume of the metal compensated from the riser. So, we have 3 stages here that is mentioned here. We have liquid, phase transformation and solid. These states are there. Let me try to just draw cooling curve for this. So, this is with time it is varying and we have temperature this side. So, it is something like temperature A, that is ambient temperature, right. So, then we have TF, this is freezing temperature, this is freezing temperature. Also, we have the pouring temperature, that is TP. Here, the cooling curve would be something, because freezing is happening here, something from here to here I will just draw a constant temperature and there will be variable temperature from Tp to 2F, then it will be falling down to Ta, that is ambient temperature. This is Q latent here, right. To calculate this total shrinkage of metal, this is equal to liquid plus solidifying. These are all shrinkages, liquid shrinkage, solidified shrinkage plus solid shrinkage. So, this, as you have seen in the previous lectures, this is compensated by providing riser, provide riser to compensate this. So, this is shrinkage that is adopted in the pattern. Now, total volume of metal compensated from the riser, it is asked, volume of metal compensated from the riser. So, adopted in a riser is only liquid shrinkage plus solidifying shrinkage. So, this is 3% given, this is 4% and this is total compensated by the riser is 3 plus 4 is equal to 7%. So, this was a very small statement that we try to see here. Another problem statement is there, where it is said grey cast iron block of dimension 200 millimeter into 100 millimeter into 150 millimeter is to be cast in sand molds. Shrinkage allowance for the pattern making is 1%. What is the ratio of the pattern to that of the casting? So, it is given here the shrinkage allowance. So, with 1% of shrinkage allowance, we have the dimension. For example, it is given here right. So, this is I would say height, length and breadth. So, it is given 200 into 100 into 150, that means length into breadth into height is the volume, which is given as 200 into 100 into 150. Now, the question is, what is the ratio of the pattern to that of the casting? So, shrinkage in each of the direction is 1%. So, simply if I say volume of casting block, volume of casting block, that is length into breadth into height, which is 200 into 100 into 150 millimeter cube. Now, it is given it is grey cast iron block. Grey cast iron we know expands on cooling. So, this expands on cooling. So, therefore, let us see the volume of the pattern. Volume of pattern, I will put it as Vp. This is equal to length minus shrinkage, that is 200 into 1 minus 1 by 100. So, this is 1%, right. This into the breadth compensation, that is 100 into 1 minus 1 by 100. This into the height compensation, that is 150 into 1 minus 1 by 100. So, in a way this turns out to be the same volume, that is 200 into 100 into 150, this times 0.99 to the degree 3. So, this becomes, so this gives me volume of the pattern over volume of casting is equal to 0.99 part 3, which is equal to almost 0.97. So, this is the ratio. So, accordingly we need to understand and design the pattern size. So, similarly there is another problem statement that also asks about the ratio if a cubical casting of 15 millimeter size undergoes volumetric solidification of 4% and volumetric solid contraction of 6%. You see solidification of 4% and solid contraction of 6%. There is no riser used and pattern making allowance is not considered. So, these are both ignored. What is the final size of the casting? This is an interesting problem statement, just go through it. So, there is a cubical block. If I suppose draw this block is a cubical which all the sides equal, let me say side is A, all the sides are A only. So, it is given A is equal to 50 millimeters and 4% shrinkage, 6% in solid contraction. So, 4% is solidification shrinkage, 6% is solid contraction. Just try to solve this problem. I will just give you a hint here and I will just give you the final answer. The volume of the casting here is, volume is A cube. So, volume of the casting after solidification, I would put it at volume of the casting dash, that is volume after solidification. This is equal to the volume of the casting into 1 minus 4 by 100. Similarly, you will find the volume in the solidification phase. This would be 1 for the volume after solid contraction. You will compensate it here. I will put it as Vs. So, you will compensate it the 6%. 6% over say compensation or contraction, whatever you told, because riser and pattern making allowance is not considered, 6% contraction will be used here. Try to use this, then try to see what does your, I would put it as A dash cube, what does this turns out to in relation to the A cube. So, this is my ratio, I will put it as the ratio R. So, this you will calculate. The answer to the problem here, that is the A dash value would be 48.317 millimeter. You will solve this problem statement by yourself, you will find the solution in the lecture notes. If still you feel some issue, then you can come for the live session that would be there, where the tutorial for in the forum you can also ask the questions. So, there is another problem statement where we design a pattern for casting having dimension length 200 millimeter, width 100 millimeter and height 80 millimeter. Casting is made from steel. Standard shrinkage allowance for steel is given 20 millimeters per meter. So, again we have been given length, breadth and height. I will try to solve this problem. Just length is 200, breadth is 100 and height is 80, all in millimeters. So, for steel standard shrinkage is given 20 millimeter per meter. For each of them it is again very simple problem, because it is length into breadth into height and shrinkage is given 20 millimeters per meter, which means shrinkage is equal to 20 millimeters per meter. which is equal to 0.02. So, we need to design a pattern for this. So, to design the pattern, I will put L dash, B dash, H dash be the dimensions of the pattern. So, L dash would be the size that is required plus the shrinkage compensation, that is 200 into 0.02. Similarly, B dash would be the size plus the compensation. Similarly, the height of the pattern would be 80 plus 80 into 0.02. So, this gives me 204, 102 and 81.6 millimeters each as my length, breadth and height of the pattern. Okay, let me add one more thing here. Let me say my pattern is something like this. This is length, breadth, height that is given. I also have, it is given diameter here. I also have a circle here or a cavity here, that is also given. So, here we will have negative allowance. Here. So, in this case, suppose if d dash is to be calculated, so this would be d minus 0.02 into d. So, I am subtracting this. So, if it is suppose given diameter is also 80 millimeters, I will put it as d is equal to 80 millimeters. So, then this d dash becomes 80 minus 80 into 0.02, this is equal to 79.84 millimeters. So, then we can design this pattern for this casting, where we have L dash, B dash, H dash and D dash as the dimensions. Let me now come to the next kind of the problem statement, which talks about the solidification time. Whether casting is pure metal or alloy, solidification takes time. The total solidification time is the time required for the casting to solidify after pouring. This time is dependent on the size, shape of the casting by an empirical relationship known as Shorinov's rule. It states that the solidification time, that is TTS, time required for casting to solidify after pouring, is equal to Cm, that is a constant, into the ratio of V by A, where V is volume of casting, A is surface area, to the power n, where n is exponent with typical value 2. It is proportional to the volume, it is inversely proportional to the area of the casting. Let us go through a problem statement. With a solidification factor of 0.97 into 10 to the power 6 seconds per meter square, the solidification time in seconds for a spherical casting of 200 millimeter diameter is, this is to be calculated. So, solidification factor K, that is given as 0.97 into 10 to the power 6 seconds per meter square. Diameter of spherical casting is 200 millimeters. I would say D here is 200 millimeters, or I could even say it as 0.2 meters. Solidification time T. T, just going through this relation, this we need to calculate time T. T, solidification time, is equal to Cm, which is also denoted by K, this times the ratio of volume to A, and I am putting the value of N as 2 here. So, here V by A, the volume to the area is pi by 3. Actually, the volume is 4 by 3 pi r cube, right, because it is spherical casting, and area is equal to 4 pi r square. The ratio V by A turns to be 4 by 3 pi r cube over 4 pi r square. This is equal to r by 3. So, therefore, this term becomes value of Cm or K, that is 0.97 into 10 raised to power 6 times r by 3 square. This is equal to 0.97 into 10 raised to power 6 into r is 200 by 3 squares. This gives me time as 1078 seconds. This is another problem statement just similar to this that you will go through by yourself. The spherical drop of molten metal with a radius of 2 mm solidifies completely in 10 seconds. Radius 2 mm, spherical drop, again same concept will be used. R is 2 millimeters, completely solidifies in 10 seconds. I would say T1 is 10 seconds. Using Shorinov's rule, determine the time required for a similar spherical drop with a radius 4 millimeter to solidify completely. So, I put T1 because I am talking about the drop 1. Drop 1, I have drop 2. For drop 1, time is T1 is 10 seconds. For drop 2, time is to be determined. So, radius of the first drop is 2 millimeters, radius of the second drop is 4 millimeter. So, we just need to calculate the ratio between T1 and T2. So, using the proportional relationship, that is Ts, where it is denoted by T. This is proportional to V by A square. So, for both of them, we can take this ratio. If it is proportional to V by A, that means T1 by T is equal to R1 by R2 square. Using this, just calculate the value of T2. The answer would be T2 is equal to 40 seconds. You will find this solution in the lecture notes, go through it. First try to solve it by yourself, then I would suggest you to go through it. Okay, another problem statement needs the volume to be calculated separately. This is a casting of steel under certain mold conditions. The mold constant in Shrovinov's rule is known to be 4.0 minutes per centimeter square. Just see the units, we need to convert it. Based on previous experience, the casting is flat plate whose length is 30 centimeters, width 10 centimeter, thickness is 20 centimeters. Determine how long it will take for the casting to solidify in minutes. So, it is asked in minutes, that means minutes will stay as minutes here. So, we have been given here the value of K is equal to 4 minutes per centimeter square. Dimension of the casting is given, length into breadth into height, this is equal to 30 into 10 into 20, this is all centimeter cube. Time to solidify, I'll put time to solidify. This is equal to K times V by A square. This is equal to K is 4, volume is length into breadth into height by area. So, this is a flat casting, just I drew in the previous numericals. Separately we have to calculate the surface area. Surface area this, then surface area this, then surface area this. All the surface areas. That means we have the surface area in both the directions, the total surface area. If I say this is height, this is length and this is breadth, so this becomes 2 times length into breadth plus breadth into height plus height into length. So, this gives me value as 4 into 30 into 10 into 20 by 2 times 30 into 10 plus 10 into 20 plus 20 into 30. So, the answer that I get is 29.75 millimeters. So, this is the time it takes for the casting to solidify. Very similar problem for a cylindrical casting is given now. Determine the ratio of the solidification time for a cylindrical casting where the height equals radius to that of the spherical casting with radius twice the radius of the cylindrical casting. Wonderful problem. So, we have a cylinder whose height is all equal to radius. So, we have height and this is radius, here h is equal to r, right, and we have a sphere. Here this dimension, the radius is 2 times r, radius is twice the radius of the cylinder. We need to determine the ratio of the solidification time. So, we need to find TTS for cylinder by TTS for sphere. Only you need to calculate, it is directly given here. So, you will only use h is equal to r, this is one thing, radius is equal to 2r, then also you will use radius is equal to 2r for the sphere. Simply you can calculate here this ratio. So, this ratio you will calculate, you will put V by A, I would put for cylinder by V by A, I will put for sphere. This ratio you will calculate. So, this is for cylinder for sphere. This ratio will turn out to be 0.14. Just calculate it. Make sure that for the volume in the area of the cylinder you put h is equal to r, and for the volume in the area for the sphere you put the radius as 2r. So, all the variables would be cancelled, you will get this ratio, this solution you will get. Next, I will talk about the riser, sprue and gate design. Using the solidification time or the volume ratio and the volume to area ratios, let us try to see another problem statement where we will design a riser. A spherical riser is to be designed for a sand casting mold. The casting is a rectangular plate with dimensions length 200, width 100, thickness 18 millimeter. Total solidification time of the casting is 3.5 minutes. Determine the diameter in millimeter for the riser such that the riser takes 25% longer to solidify than the casting. So, we have been given here length breadth, height as 200, 100 and 18 millimeters respectively. You call it height or you call it thickness, it is given thickness here. Total solidification time is TTS is given here 3.5 minutes. For the riser, they say it takes 25% longer, which means TTS, I will put it as R for riser, this is equal to existing time plus 25%, which is equal to 3.5 into 1.25, it is 25% rise. Now, for sphere, the V by A is equal to 4 by 3 pi r cube by 4 pi r square, that is equal to r by 3, this we have discussed. So, the solidification time TTS is equal to K times V by A square, which means 3.5 is equal to K times for the plate, like we saw in the previous numerical, length into breadth into thickness over 2 times the over the total surface area, that is 2 times into 200 into 100 plus 100 into 18 plus 18 into 200. This gives me the value of K, that is the constant, as 0.5. Now, for the riser, time for solidification is 3.5 into 1.25. This is equal to K into r by 3 square, which means 3.5 into 1.25 is equal to value of K is 0.5 into r by 3 square, which gives me the value of r square as 78.75, and I get the value of r as 8.87 millimeters. Just see, we have calculated value of K and used it here. This is the riser design. I will go more deep into the sprue and the gating design in the next part of this tutorial, and will continue the discussion the casting problem statements. Thank you.